Good evening, everyone. So in today's session, we'll be discussing questions about name-based SQL, PCA, and some basic probability concept. So for the probability distribution, one of the important part is this probability density estimation. So always it's like when you have some observed data, that means you have say n data point. Then the question is, what is the distribution that most likely generated this n data point? So there are so many distributions. For example, we have in the lecture, we like the professor talks about Bernoulli and also Gaussian. The reason why these two are considered is because they have less number of parameters. For example, Bernoulli has only probability, and Gaussian has only mean and the variance. So these two are considered. Now, in these two, there are some parameters, like I told, either the probability or the mean and the variance. These parameters, they need to be estimated. Right? So this so the first way to find the distribution that most likely generated the data points is the first one is the frequentist approach, and the second one is the Bayesian approach. So in the first approach, so for example, when we consider the Gaussian distribution, we have the mean and the variance as the parameters, but we don't know what the values of those parameters are for our data set. So we have an optimization function there that we want to maximize or minimize, and then we estimate these parameters. So that is what is done in frequentist approach, where we find the parameter value that maximizes certain certain things. For example, here it maximizes, as mentioned in the video, the maximizes the likelihood, which is the probability of generating these data points given certain parameters. So this is one way of finding that density estimation by frequentist approach. Now there is another way, which is the Bayesian, where we already say a prior distribution. We already specify a prior distribution. And then we update to the posterior, or we update the posterior using the Bayes theorem. So an example of this approach you will come across, I think, in the next week or the week after, which uses this concept, that is the VAE, the variational autoencoder. So the variational autoencoder assumes the prior distributions and then update the posterior by finding some by optimizing how close the prior is to the posterior. So there is some optimization that happens there. So this is one example where you can see this is one example where you can see that you trying to find the distribution that most likely generated the data given some data points, given say n data points. So then so these are the two approaches. Then in the lecture video, the professor talks about Bernoulli distribution. So Bernoulli distribution it models a single binary variable. So for example, when x is equal to 1, which denotes head, has probability mu, then x is equal to 0, which denote tail, the probability will be 1 minus mu. So this probability value will be a value between 0 and 1. Now for the Bernoulli distribution, the probability mass function is given by mu raised to x into 1 minus mu the whole raised to 1 minus x. So x is the value, that is either head or tail. Mu is the probability. So if it is an unbiased coin, it will be 0.5. Otherwise, it will be some extreme value for head or tail. Now for this one, the mean and the variance is given by mu and mu times 1 minus mu. So now when we consider a data set, say it is having points, n data points, x1, x2, etc., okay, xn. So this is flipping a coin. You observe these many results by flipping a coin. Then the likelihood, that is the probability of the entire data set as a function of mu. So this is the data set B. This is given by the likelihood function, which is the product of so this is the probability that the probability of this entire data set as a function of mu. So this is the likelihood function. Now we want to maximize this. That is, we want to find a distribution that will tell us or that will model how the data is generated. So here we have the product. So to convert for easy calculation, we can convert it to sum. Now for that we can take log, because when you take log, this multiplication will be converted from this multiplication to sum. So then we take the log of P of D by U, which is sigma. So when we take the log, this product part this will become sum. That is why this sigma here. Then when you take log of this, it will become xn log mu, xn log mu plus this multiplication becomes plus 1 minus xn times ln of 1 minus mu. So this is the maximum likelihood. So we are maximizing the log likelihood. Now, when you say we are maximizing, what we do is we uh, take the derivative of this with respect to mu. That is d by d mu we take. And then when we do this, we get mu as 1 by n, sigma n from 1 to n xn. And this is equal to m by n, where m is so this is simply the fraction of whatever we have assumed as x. So if I assume the x as the x as head, then this will tell me the fraction of x. Or is it's like uh, the probability that you get head. So this is the fraction of head. So this is one thing that is explained in the video. Now, for binomial distribution, it will count the total number of heads among. So if I have n flips, it will count the total number of heads m in the n flips. So the binomial PMF, we know that it is this n factorial by n factorial n minus m factorial. So for that, the mean will be n times mu and the variance will be n times mu into 1 minus mu. Now, when we consider Gaussian, so this is one probability distribution that is very commonly used for modeling continuous variable. The other one was the other one was for discrete variables. Yeah. So in case of binomial, so here you have only one flip, but in case of binomial, we consider the total count of m heads in m flips. So when we consider the binomial PMF, what do we have? N factorial divided by m factorial into n minus m factorial into mu raised to m plus 1 minus mu raised to n minus m, right? So this is the probability of getting m heads. This is the for binomial distribution. This is the probability of getting m heads. So the for the mean and the variance, the equation is given by n times mu, and the variance will be n times mu times 1 minus mu. So this is for binomial distribution. Okay. So before we were modeling each flip individually. So here we are modeling each flip individually, but here you are taking the total n flips, and we are taking the total count of that many flips, n heads also. Now, in case of Gaussian, this is one of the most commonly used for continuous variable. So in when we have 1D Gaussian, that is when we have a univariate Gaussian, This the equation is given by, I think you all will be knowing this. So the equation of Gaussian will be given by this form, and mu is the mean, and sigma square, this is the variance. So when you have very small variance, you will have a very narrow bell curve, and when you have a wide variance, we will have a wide bell curve. So this is for the 1D Gaussian, and then you have D-dimensional Gaussian. This is given by, so instead of variance, here we have covariance. So this is the determinant of the covariance matrix, and then exponent. So this is the d by d. When you have a d-dimensional version, this is the d by d covariance matrix. This is the determinant. As if you have gone through the Bishop's pattern recognition textbook, you can see that they explain that this sigma must be positive definite for this Gaussian distribution to properly form. So you can read that in detail there. So now in the video they talk about those three different curves. So there is something called as, that is the delta square is 6 minus mu the whole raised to t minus mu. So this is the Mahalanobis distance, and when this sigma value, if it is I, that is an identity matrix, then this is equal to, have you come across this distance anywhere? So when the covariance is identity matrix, this is equivalent to Euclidean distance, x minus mu the whole square. Okay. So when this is a diagonal matrix, the covariance matrix is diagonal and also non-diagonal. There are two possible cases. So when this is diagonal and sigma 1 square is equal to sigma 2 square, then this contour will be circle in the d-dimensional space. So this is what is explained in the video. Explaining, I think there was one previous year question also. So when these are equal, it forms a circle. I think when you substitute it here, you can see that it forms a circle. And then when it is sigma 1 square not equal to sigma 2 square, then it forms an ellipsoid. Now, when we have a non-diagonal covariance matrix, in that case, we get tilted ellipse. Again, it is ellipsoid, but we get tilted ellipsoid. So this is what is explained in those video. And also, so in detail, if you want to read about this, you can check Bishop's pattern recognition textbook. This is also mentioned as one of the references in the video. So you can check that. Now, there is one question. So this is one previous year assignment question. So when estimating the parameter mu for a Bernoulli distribution using maximum likelihood estimator, what is the formula for this mu value? Is it n by m, n by n, 1 by n, m squared by n? Yeah, so it is m by n. When the covariance matrix of a multivariate Gaussian distribution is proportional to the identity matrix, what shape will the contours of constant probability density have? So it is square into I, that is sigma square into 1001. So then this is sigma square 0, 0, sigma square. So these two are equal. So it will be a circle. Now coming to Naive-Bayes classifier. So you have x. X is a set of features. Let them be x1, x2, etc. to xd. Here we have class. In general, we are representing it by C. So the equation, so here as I mentioned, this when you substitute, when the covariance matrix is an identity matrix, you get x minus mu into x minus mu. And when you have the diagonal matrix, and when the diagonal values they are equal, the contour will form a circle in the d-dimensional space. That is why when sigma square into 1001 came, it is equal to sigma square 00 sigma square. These values are equal, so it is a circle. So we have a class C. Then we have to find the posterior probability of each class C. Given some features or given some value of the feature, let it be given x. So that is represented by probability of C given x. Now by Bayes theorem, we know that this is probability of x given C into probability of C divided by probability of x. So this probability of x, that is the same for all classes. So we only maximize the numerator. And when I think this is mentioned in the video, so we ignore that part and we only maximize the numerator. So here the naive assumption is that there is conditional independence between the features given class. That means we can write this as this probability of x given C. If we say there is conditional independence, then we can write it as a product, right? So we have D features, so probability of xi given C. So this is the main thing that is used in Bayes classifier, that you assume the naive assumption is that there is conditional independence between the features given a class C. And the final posterior probability is the one that maximizes this part. That is probability of C into product of I from 1 to D probability of xi given C. So we take the maximum. So we take the argmax of this, and this is the maximum posterior probability that we get. So this is what we do when we have a certain set of features and we want to predict the class for that features. We calculate the class probability uh, given certain feature. So if we have two classes, we calculate for class 0 and class 1 given certain feature value, and then we take the class which has the maximum probability, that is by this R max. So one issue that is mentioned in the video is about Laplace smoothing. So sometimes some features might have zero values. In that case, we can add a add a value 1 to the numerator. So if we add value to the numerator, we should also if we add 1 as a value to one of the features, we should also consider other features. So as mentioned in the video, there's a formula that you can use to prevent this situation, and that is called as Laplace smoothing. Okay. Mm. Now coming to principal component analysis. Mhm. Mhm. So, central limit theorem, we all know that as the n value for an n value tends to infinity, the sample mean will converge to Gaussian. So, as the n values increase, the mean converges to the Gaussian distribution regardless of the original distribution of xi. So, according to the central limit theorem, what happens to the distribution of the sum of n? It becomes increasingly uniform, it becomes increasingly Bernoulli, it becomes increasingly Gaussian, it becomes increasingly Poisson. Yeah, so it becomes increasingly Gaussian. So the formula for Laplace smoothing, this is, so if I have a feature xi and it has a value say v and given t, what it does is the Laplace smoothing, it uses the count of xi is equal to v comma c plus 1 by the count of that specific class C plus n. N is the number of unique values of this feature xi. This is the formula that is used for Laplace smoothing. It's given in the video, so you can check that. When using a naive-based classifier for prediction, what rule is used to assign a class to a new observation? Minimum error rule, maximum a posteriori rule, minimum distance rule, maximum likelihood rule. Yeah. So the maximum a posteriori rule is used to assign a class to a new observation. Given a dataset with features X and classes C, the naive-based formula P of C given X proportional to P of C into the product of P of Xi given C is derived by applying which of the following? Central limit theorem and independence assumption, Bayes theorem and conditional independence assumption, maximum likelihood estimation and uniform prior, chain rule and joint probability assumption. Yeah, so it uses the concept of Bayes theorem and conditional independence assumption. Mm, Okay. What is the probabilistic interpretation of the least features cost function? It maximizes the posterior probability of the parameters. It minimizes Bayesian error rate. It maximizes the likelihood of observing the data given the parameters. It minimizes prediction variance. So this is something that is explained in the video. So you have the least square cost function, and so that has the format sigma yi minus f of xi comma theta the whole square. So so this is given in the maybe I'll try to upload the solution, or the other TA is already uploading the previous year assignment solution. So you can check that also. So in that assignment solution, they describe this. So j of theta is sigma yi minus f of xi theta the whole square. So we model the variable, the target variable as f of xi comma theta plus some error value. And this noise, it is assumed to be Gaussian noise with zero mean and variance sigma square. So when we do the likelihood, which is the product of and then we take the log likelihood, and when we maximize the log likelihood with respect to theta, it will be equal to minimizing the sum of square error terms. That is this one. So that's why, so minimizing the least square cost function is equal to performing maximizing the likelihood of observing the data given certain parameters. So the least square maximizes the likelihood of observing the data given the parameters. Okay. Now, coming to principal component analysis. Uh, so one main reason behind this is dimensionality reduction. As we have large number of features, the issue is we need large number of data also to get a better prediction. So high dimensional data is an issue unless we don't have a large amount of data as well. So PCA finds or it project to a different lower dimensional space. So if they have a higher dimensional data set, PCA will project it to a lower dimensional space. Now, how it projects this? By finding the direction or by finding components along which the data varies the most. So we find the direction along which the data varies the most. So I have come across one blog. I couldn't find it later. So there was a blog that talks about really why you want to use PCA and why this uh, direction along which the data varies the most is important. So they talk about you have been to some forest and you want to categorize different types of birds in that forest. And you have different types of bird and the birds have very different features. Some will have different types of color, different type of feather, so many things. Uh, the features are different. And so all these features are one of the dimensions in our data. So x1, x2, etc. up to xn. Now, we want to find, so there will be a lot of redundant features. So for example, if all the birds in that forest, if they all are in yellow color, then the feature color doesn't contribute or it doesn't give us any information. We can't categorize the different birds based on the color because all the birds have yellow color. So we can't use color as a feature that can distinguish the different types of birds. Now, this is why we say finding components along which the data varies the most. So we have to find that feature along which the data varies the most. That is, having one color means there is no variance or almost very less, almost no variance or uh, sorry, no variance at all. So having one color is no variance, but if I have 10 colors, then that means that there is some variance, right? So this is why we tell when you have feature that contains or that varies a lot, that might contain enough information that can help you classify. That is why we find the components along which the data varies the most. Um, so now this PCA, this is connected to something that we have already studied in the beginning, that is the eigenvectors and singular value decomposition. So the PCs, the principal components, these are the direction along which the data varies the most. Okay. So these are the eigenvectors of the sample covariance matrix. So how do I get this sample covariance matrices? For example, if I have say two features, x1, x2, and the values are 1, 3, 3, 5, 5, 6, 8, 9, 2, 3, 5, 4, 6, 5, 7. Now, when we calculate, so we know how to calculate covariance. First, we find the mean and mean of this one, 1 plus 3 plus 3 plus 5 plus 5 plus 6 plus 8 plus 9. So that will be uh, 40 divided by 8 and it will be 5. Similarly, for x2, we find the mean and that will be also 5. Now, once we have this, we find the x1 minus x1 bar. That is the variance. X1 minus x1 bar the whole square divided by n. So you take each of this x1. So 1 minus x1 bar, which is 5, the whole square. That is 4 square, 16. That is divided by 8. So like this, when you do this, you finally get 50 by 8, and that will be around 6.25. Now this is for just x1, and then you have x1 minus x1 bar and x2 minus x2 bar, sorry. And this will be the covariance between x1 and x2. And when you calculate this and put it here as a diagonal matrix, this will be around 6.25, 4.25, 4.25, and 3.5. So this is that sample covariance matrix that we estimate when we have a data set like this. So this is the covariance matrix that we have. So once we have a covariance matrix, then we can find their eigenvalue. So we have this equation number times x. So from this we can find the eigenvalues and eigenvectors of this covariance matrix. And these eigenvectors are the principal components. Now, uh, so, so one way to do this decomposition into um, eigenvalue, eigenvector is this eigenvalue decomposition. Another is HVD, which will work for rectangular matrices. So we may not always have square matrices. Our data set will be always rectangular. It will not be a perfect square. So HVD works for rectangular matrices. And you have this in XVD, you have this USV transpose. This is the left singular vector, the right singular vector, and the final singular vector. So when we do the singular value, we usually use singular value decomposition to find to do this PCA. Now, there are some steps that we always do, like we subtract the mean. So we center the data because we want all features to have a mean of 0. And then we apply the singular value decomposition. And once we have the singular value decomposition, we arrange them by their the singular values or the eigen value that we get, and then uh, we take the ones, we take the eigenvalue that explains maximum variance. Now, how do we find this explained variances divided by? So, for a principal component K, the explained variance, that is, so you have this n number of features, x1, x2, etc. up to xn. You want to reduce it to m dimension, which is x1, x2, etc. up to xn, and m is less than n. Okay, you want to reduce it to a lower dimensional space. Now, when you reduce it to a lower dimensional space, the principal components, that is the components that tell you the direction along which the data varies the most, that will have combinations of these different features. So then, it will have PC1, PC2, PC3, etc. So it will create certain components that will have a combination. So what I mean by combination is, for example, if I consider 2D data, this is my x1, this is my x2. So suppose my data is like this. These are my points. Now, the direction along which the data varies the most is this, right? This is the direction along which the data varies the most, not this direction, right? In this direction, it doesn't vary most, but in this direction, it varies most. And if you see this line, this is a combination of x1 as well as x2. That's why I meant by some combination of different features will be this PC1, PC2, PC3. Now, we have to find uh, how much of the variance in the data is explained by this PC or the principal components. So we can take the first principal component, second principal component, third principal component, sum them, and then find how much of the variance is explained by these components. If usually if it is 95% or more, then so if PC1 and PC2 is they together they together, when you sum this, they together contributes 95 percentage of variance. Then that means using just PC1 and PC2, you can represent the full data set which had actually n features, but now you need only 2 features. So n is 10, and then you reduced it to PC1 and PC2. Instead of that, x1, x2, etc. up to x10. So this is the explained variance, and the sum of this, if it constitutes to around 95 percentage or 90 percentage, then you can tell that the data is well explained by these principal components, and you can use that instead of the higher dimensional features. The main reason why we are able to reduce it to a lower dimension is that there might be redundant information in the data set. Some features might be correlated to each other. So, for example, here also when x1 is increasing, x2 is also increasing. There is some correlation. So with principal component, we can remove that correlation. So it removes the redundancy. That is, it will correlated features can carry duplicate information. So that is removed by this. Yeah, so this is the use of principal component analysis. Now, from previous year question, what matrix factorization method is typically used for PCA? QR decomposition, LU decomposition, singular value decomposition, solid-state decomposition. Yeah, so this SUV. Okay, now coming to support vector machine, it is one of the supervised classifier that will find an optimal separating hyperplane. That is, if I have optimally separating hyperplane means, suppose if I have apples versus oranges, then you are, so these are the two classes that I have, and then you can have a decision boundary either here, or you can have one here, or you can have one here, uh, or you can have one like this, or you can have one like this. It can be anywhere. But what the support vector machine does is, if you find a optimally separating hyperplane, that will find the line that is maximally far from all the data points from both the sides. So it's, so it will find the decision boundary that is maximally away from the points on both the sides. This is the margin, and this margin will be maximum. That is how it finds the uh, line that classifies the two different classes. So here mainly they talk about a linear classifier. So a linear classifier, the model will be a line. So when you have model as f of x, this will be given by W transpose x plus b, like our mx plus b equation for a line. And if f of x is greater than or equal to 0, then it is class 1. If f of x is less than 0, then it is class -1. So this is how we describe the classifier. Okay. So in SVM, what happens is this margin. This is the distance uh, from the decision boundary to the nearest training point on each side. So on each side, they take the nearest training point, and these nearest points, they are actually called as support vectors. These are called as support vectors. So the optimal boundary depends on this nearest points, and these are called as a support vector. Now for SCM, the margin formula is given by 2 by. So this is the equation. So this, I think in the video also they say that this is the distance of the point to a distance of a point to a line, and this is given by this equation. So what you have to, so for easier calculation and all, the hard margin SVM, it works. I mean, the optimization part is you have to minimize. So you have to actually maximize the margin, but this is also equivalent to minimizing this norm square subject to W transpose xi plus b greater than or equal to 1, where yi is 1 or minus 1. So when yi is plus 1, for this equation, we get W transpose xi plus b, and this is greater than or equal to 1. When yi is minus 1, then this is W transpose x plus b greater than or equal to 1, because you multiply this by minus 1, the negative will become positive. So it is again greater than or equal to 1. So this is the objective function for the support vector mission. Now, there are some other types also. So, in case of like here, we only use the linear formula, but then there are other types of FEMs as well, like the one that uses some kernel tricks. So that is what that does is it will project the data to a another dimension, and then it will follow the same rules. So it uses something called as a kernel. So for one example is the Gaussian. So it will project the data to that dimension using this Gaussian kernel, and then it will do the classification. Yeah. So one previous year assignment question: how is a decision boundary mathematically represented in a support vector mission? W transpose x plus b is equal to 0. Y into W transpose x plus b is greater than 1. W transpose x plus b is greater than 0. Sign of W transpose x plus b. Yeah, so yeah, I will tell why the condition is same. So for W, sorry, for support vector machine, this so you had those line and the boundary. Right? So this line equation is given by W transpose x plus b is equal to 0. And this is W transpose x plus b is 1. So everything that is greater than this is class 1. Everything that is here is class minus 1. So it has to maximize the margin between this hyperplane or the line and the nearby data points on both the sides, on both the classes. So you have this two equation that you have to satisfy. W transpose x plus b is 1, and also W transpose x plus b is minus 1. Okay. So now you have to satisfy both the equation, right? To classify whether a point correctly fall on this side or on this side. This needs to be correctly classified, and if that needs to be done, we need a way to represent both the equation, right? So that is why we represent it as y into W transpose x plus b greater than or equal to 1. So this will satisfy both the cases where when y is equal to plus 1, we need W transpose x plus b greater than or equal to 1. And when y is equal to minus 1, we need W transpose x plus b less than or equal to minus 1. So both the things will be satisfied by this equation. So this two condition, this can be represented by this equation. That is why we write it this way. Uh, so the answer is B, which is y into W transpose x plus b greater than or equal to 1. What constraint is applied to ensure data points are correctly classified by NFP? Sorry, I was explaining the question there for both cases yi is equal to plus 1. Condition is same. Here they have not, that is the next question. So here they have asked what is the decision boundary. So the decision boundary is W transpose X plus B is 0. This is the decision boundary. The next question, what is the constraint that is applied to ensure data points are correctly classified? Yeah, so this is y into W transpose X plus B greater than 1. So in the naive-Bayes classifier that is trained on a data set where the feature outlook is equal. So there's a data set and outlook is one of the feature there. And the value, one of the possible value for this outlook is overcast. And this is something that never co-occurs with the class play is equal to no, which statement correctly describes the consequence and the standard fix. So the classifier assigns an infinite score to play is equal to no. The posterior score for play is equal to no becomes 0 due to 0 conditional probability. Fix it by applying Laplace smoothing. The classifier becomes undefined. The MAP rule automatically ignores 0 probability features. No fix is needed. Yeah, so the posterior score for play is equal to no becomes 0 due to 0 conditional probability, and we have to fix it by applying Laplace smoothing. In principal component analysis, this statement correctly explains why truncated SVD achieves dimensionality reduction. Truncated SVD discards the column of the data matrix corresponding to the largest singular values, since those directions carry the least unique information. Truncated SVD retains only the k largest singular values and their corresponding singular vectors, projecting the data into the k directions of maximum variance. Truncated SVD normalizes each features to zero mean. Truncated SVD removes highly correlated features by computing the eigenvalues of the original data matrix directly. Yeah, so as I mentioned before, when we have those, so when I had n is equal to 10, and when we made it to two principal components, we take the largest two principal components and their corresponding vectors, and then we project the data to those k directions of maximum variance, because that was explaining 95% of the variance in the data. So I don't need to uh, use the rest of it. And that's why the truncated SVD achieves dimensionality reduction. So an SVM is trained with weight vector W is equal to 2 minus 1 and bias is minus 3. New point x is equal to 4, 1 is given. What is W transpose X plus B and what class is predicted? So W transpose X is W is 2, uh, sorry. So W transpose X is W is 2 minus 1 and X is 4, 1. So when you take the dot product, 2 into 4 plus minus 1 into 1. So that will be 8 minus 1, 7. Then B is minus 3. So W transpose X plus B is 7 minus 3, which is 4. So 4 is greater than or equal to 0, greater than 0. So it is class 1. A data set has 500 samples and 50 features. After applying SVD, the singular values are 120, 85, 40, 12, 3, 1, 1, etc. up to 1. A researcher wants to retain 95% of the total variance. Which of the following actions is most appropriate? Retain all 50 components because dropping any will lose information. Retain the first 3 since the remaining value dropped sharply, suggesting those 3 directions capture most of the variance. Retain the last 47 components because they correspond to the fine-grained details. Retain only the first components because it is the largest. So, before I explain this explained variance, which is lambda I by sum of all the lambda I, but here lambda k for a specific kth eigen, kth PC component, lambda k by sum over all the eigenvalue. So, here it is eigenvalue and what we have is the singular value and the singular value is the uh, I mean the singular value square is the lambda value. So here what you have to do is we have to take the square, the sum of the squares. So that is I have say 120, 85, 40, 12, 3. Remaining all are 1. So 1, 2, 3, 4, 5. So remaining all are 1. So here what you have to do is you have to take 120 square. So here one question is this: retain the first three components. So that means 120 square plus 85 square plus 40 square, the whole divided by the sum of all this square. So when you do this, we will see that this will come around 99.1. So that means this is well above this 95 percentage of variance that the researcher wants to retain. So the answer is retain the first three components because uh, these three direction capture most of the variance. In SVM, the margin is given by 2 by the norm of W. To maximize the margin, what optimization is performed? Yeah, so you have to maximize the margin, and the equation of distance of a point to a line is given by this 2 by norm of W. But maximizing 2 by the norm of W, this is equivalent to minimizing the norm. And for a mathematical convenience, like for smooth gradients, when we use the gradient difference and all, so for smooth gradients, this is usually written as 1 by 2 norm W square. So this is uh, done for the gradient convenience for calculation of gradients. So that is why it is minimizing 1 by 2 of W square. So what are support vectors in an SVM? All the training data points, the data points that lie closest to separating hyperplane, the weight vectors W and V, misclassified data points. So support vector, these are the specific training points that lie exactly on those boundaries. Uh, so these contribute a lot to the final optimal hyperplane that we get for classification. So the data points from each class that lie close to the separating hyperplane. Mhm. So in SVM, the class labels are +1 and -1 rather than 1 and 0. Why? To ensure the weight vector W has unit norm, because it simplifies the constraint into one single inequality. To make the cost function effective, because neural network requires symmetric labels. Yeah, so it will simplify the margin constraint into one equality, that y into w transpose x plus b greater than or equal to 1. And this is one of the foundation of SVM optimization. So how does linear SVM relate to logistic regression? Both model output probability score between 0 and 1, both find linear decision boundary, but SVM explicitly maximizes the margin, whereas logistic regression does not. SVM is a special case of logistic regression. Both use Rosen-Robbie for loss. So this SVM explicitly maximizes the margin. So what is one of the important problem that PCA primarily addressed in machine learning? So overfitting caused by too many training samples, high dimensionality of the feature space, class imbalance in training data, slow convergence of training data. So high dimensionality. So that's a data set. And it has three features and five data points. They did SPD and the singular values are 9, 7, 0. How many meaningful principal components are there? So the principal component, the singular values are 9, 7 and 0. How many of them are meaningful? So here you can see that one of the singular value it is 0. That means that there is no variance that exists along that direction, or that feature is not at all contributing anything to the data structure. So only the two non-zero ones, 9 and 7, they correspond to meaningful direction. So that means that the data essentially lives in a two-dimensional space. So the meaningful species are 2, because the other one is 0, which doesn't have any variance at all. The rows of the data matrix corresponding to outliers are removed. The singular value matrix is divided into k equal submatrices, and each is analyzed separately. The rows of the data matrix correspond to outliers. The singular value matrix is divided into k equal submatrices. Singular value matrix is rounded to nearby integers. K largest singular values and their associated singular vectors are retained. So the lambda is something that comes with eigenvalue decomposition. So that is here I mentioned. So this is the explained variance for eigenvectors, and when it comes to singular value, you take the sigma square. So if you get 120, for example, we mentioned here that we got this singular values are 120, 85, 40, 12, 3, etc. We take to find the explained variance, we take the square of that and divide by the sum of all the vectors. So it is 120 square plus 85 square plus 40 square plus 12 square plus 3 square plus how many other ones are there? The square. So you get the individual contribution of each of them. So for example, how much the singular vector corresponding to the singular value 120 contributes, you take 120 square by 120 square plus 85 square plus etc. How much this one contribute? 85 square plus 120 square plus 85 square plus etc. Now, if you want to know how much the first two principal components contribute, you just sum this. That is what this is shown. So, first three principal components is what is shown here. The singular, the k largest singular values and their associated singular vectors. These are weighted. During training of nail base, what calculation is performed to estimate P, temperature equal to hot, place equal to S from the training data set with 9 S days and two of those S days are hot. So then what is this probability of temperature equal to hot, place equal to S? So here I think you meant standard deviation. I think you meant square root. I hope so. So singular values are square root of the uh, eigenvalues. Yeah, so it is 2 by 9. Yeah, because 9 yes days and out of which 2 are hot. So the probability of S given X is 0.0053 and probability of no given X is 0.0206. So what is the predicted class? What is the predicted class? Yes, because 0.0053 is small error. No, because 0.02 is greater than 0.005. Yes, because probability of yes is 9 by 4, which is large, cannot be determined. So it is the highest probability. So a disease has prevalence P of T 0.01. A test has positive result given D is 0.95 and negative given D is 0.90. What is P of D given plus approximately? A 0.95, B 0.50, C 0.01, D 0.0. We have to find probability of D given positive. This is probability of plus given D and the probability of D divided by this. So this is given, this is given. How do we find P of plus? This is given by P of plus given D into P of D plus P of plus given not D into P of D. So P of plus given D is 0.95, P of D is 0.01. Now what is P of plus given not D? P of minus given not D is 0.95. This is also given. So P of minus given no D is 0.90. So P of plus given no D. So given no D, the test being negative is 0.90 and given no D, the test being positive is 1 minus this. So it will be 0.10. Now it is, you just have to substitute all these values. So this is 0.95. D is 0.01 plus this is 0.95, sorry, 0.10. And this negation of D, that is 1 minus 0.01, that is 0.99. So once we have this, we can substitute this value here, and then P of D given plus this P of plus given D is 0.95 into P of D is 0.01 divided by this will be around 0.1085. 0.1085. So the final answer will be yeah. So it will be approximately 0.087. Then we'll see next week for section 11.